from University of Stuttgart. Outline the following motivation. Formulation will be presented, some residual stresses and fracture toughness discussion, explanation how to use, solution of the problem, some results for stress intensity factors, energy release rates, fracture angles, and critical loads, and summary will be done. Motivation. Thermal barrier coatings are used in different engineering structures. One example presented here, it's engine in airplane, and barrier coatings are made from ceramics mostly, and they are used to prevent from over melting or heating of metallic parts. Under operation, high residual stresses arises at the interface because of different thermal expansion coefficients of these materials, which leads to debonding and cracking. Some crack systems here presented here. In order to overcome this situation, special kind of composites designed, so-called fracture functionally graded coatings or functionally graded materials. The composition of these materials change continuously through thickness of coatings, and material properties also continuously changed. A series of problems was solved theoretically previously, and the main goal of this is design of improved thermal barrier coating systems, which operated on under very high heat fluxes. Here presented the mechanism of crack formation, some typical crack systems in these coatings which arises, and formulation. How we can formulate our problem? We consider thermal barrier coating as function graded coating under homogeneous substrate, and between can be considered also thermally growing oxide, and a system of cracks presented in function graded coating. They are defined explicitly by their coordinate of the centers of and inclination angles of these cracks to the x-axis, for example, if we consider system coordinates. And loading, thermomechanical loading, cooling on delta T, and tension. We calculate stress intensity factors in mixed mode K1, K2, and then using fracture criteria. Other fracture characteristic we can calculate, for example, deviation angle or fracture angle, critical loadings. And in this case, we have to know fracture toughness near crack tips. So in our formulation, we have to know effective properties of FGM, fracture toughness of FGM, which also continuously varying in width of the coating. And so we need models for this too. Very often use such models, for example, exponential function model, linear or others. In this case, non-homogeneous coefficient or graded coefficient simply defined by these formulas. Other way to do this is using one of the rule of mixtures. In this case, we consider volume fraction of inclusion phase and non-homogeneous parameter or graded parameter here, lambda in this case. Some examples how present how looks Young's modulus for different coefficients of this lambda. We use superposition principle. It means that for applied loads reduced to loads on the crack faces. It also goes for residual stresses. So we calculate residual stresses on the crack faces or other loads on the cracks due to mechanical loading applied to system FGM homogeneous. And then we we are using on construct single integral equations. Right side it's known loadings, and unknowns it's derivative of displacement jumps on the crack faces. And after solution of these equations, we calculate stress intensity factors. So in solution we have input parameters following, material properties we have to know, then calculate graded parameters, and geometry we have, and loads. Then output parameters, stress intensity factors, energy release rates, fracture angles, critical loads. So the schematically we can, this scheme of these calculations. One illustrative example is presented here for 3 edge cracks with same size, with inclination angles which vary from 60 and 90 degree, and for this combination of materials for FGMs. On the top it's ceramic, and homogeneous it's steel. Let us consider these parameters as stress intensity factor mode 1 for these 3 cracks. Here presented for crack 1 and for crack 2. Crack 3 behavior is similar. K1 is normalized by K for one crack. So what we see, less distance between cracks, less K1. So these cracks will, it means that shielding effect is observed for this crack system. It's very for this crack system, it's very often consider this situation. And also K1 for crack 2 is less than for out crack 1 and 3. It means that propagation will start from out cracks. Consider energy release rate. This in energy release rate also contains Young's modulus as a function of depth of the lens. And we consider that behavior of these two values is similar, and both D and inclination angle B get big influence on these values. Comparing K1 and critical loads for this crack system, we see that for critical loads, distance D big influence on these values, but inclination angles not so big influence. And less D, greater critical load. It means that shielding effect also observed for in terms of these critical loads. K2 responsible for crack mixity, so for deviation of the cracks of initial crack propagation, and we see these fracture angles or deviation angles, and influence of inclination beta much more pronounced than distance between these cracks. And what is shown on this schematic of 3 cracks, the deviation angles, it's just for this crack system. So cracks, out cracks will propagate out of this crack system. Considering influence of parameter lambda in rule of mixture, we see big influences of this lambda on K1 and also on critical loads. And for K2 also big influence both lambda and beta, and fracture angles also both values of lambda, both parameters of lambda and beta influence of these fracture angles. And I come to some conclusions. Illustrative examples are presented to show the influence of material and geometrical parameters of the problem of the fracture characteristic of interacting cracks. The weakest crack in the considered system is of 3 edge cracks are the outer edge cracks 1 and 3. The structural variation of fracture toughness for the FGM was taken into account. For the graded parameter lambda in the rule of mixture, it was obtained that variation of lambda leads to a significant change in the fracture parameters, in particular critical loads. On the basis of developed theoretical model, which allows to correlate the material parameters, geometrical parameters, and the main fracture characteristic, an optimization problem can be solved. For example, to find a gradation parameter and crack arrangements that maximize the thermal critical stresses, that is increasing the fracture toughness for FG coagents, function gradient coagents. So thank you for attention.